In this video, we will synthesize the classical understanding of time with the idea of timelessness, particularly through the lens of photon behavior and the implications of relativistic physics. Roger Penrose has long advocated the need to rethink our physical theories, particularly the connection between consciousness, quantum mechanics, and space-time. However, while Penrose addressed the abstract concept of timelessness and its relationship to consciousness through Platonic ideals, he failed to adequately address photons, perhaps the most direct manifestation of timelessness in physics. The concept of the extended moment offers an intriguing exploration of time, timelessness, and the behavior of light, built on the principles of special relativity. As an entity moving at the speed of light, the photon is often used to highlight the limitations of traditional concepts of time and space. In fact, within the framework of special relativity, a photon does not experience time in the same way that massive objects do. For an observer traveling alongside the photon, hypothetically, since no observer with mass can reach the speed of light, time would not pass. There would be no temporal intervals between events. From a relativistic perspective, anything traveling at the speed of light does not experience time in the same way as an object traveling slower. Special relativity shows that the passage of time slows down as speed increases. This phenomenon is called time dilation. At the speed of light, this time dilation becomes infinite, meaning that time freezes for the photon. This leads to the intriguing idea that photons exist in a state of timelessness. From an external perspective, photons traverse space-time, but from the photon's own perspective, if such a perspective existed, it would not experience the passage of time. Therefore, photons are essentially timeless. From a strictly physical perspective, photons lack internal structure or consciousness, and therefore cannot perceive in a way similar to human perception. This anthropomorphization of the photon's experience extends beyond the boundaries of physical theory and enters the realm of metaphysical speculation. One of the more compelling ideas we will discuss here is the concept of a continuum between time and timelessness, as differentiated by speed. At one end of this spectrum is rest, an object that moves only in time but not in space, like a stationary observer. At the other end is the photon, which moves in space but not in time. This continuum is governed by the interaction between the relative speeds of objects and their experiences of time, as defined by special relativity. Singularities are defined as points at which space and time become indistinguishable. In both cases, photons and singularities, the familiar distinctions between space and time break down. In the case of a black hole singularity, general relativity predicts that space-time curves infinitely, eliminating all distinctions between spatial and temporal dimensions. Similarly, at the speed of light, space and time merge differently for a photon. From the photon's perspective, they cease to exist altogether. We will continue our video by referring to the twin paradox, a fundamental thought experiment in special relativity. This paradox demonstrates the difference in aging between two twins, one stationary and the other traveling at speeds close to the speed of light. The twin traveling at relativistic speeds ages more slowly due to the effect of time dilation, which has been confirmed by experimental evidence, such as the extended lifespan of fast-moving particles or the slowing down of clocks in fast-moving airplanes. What does time dilation mean? While the physical meaning of time dilation is clear from the equations of special relativity, this question requires a deeper, more intuitive understanding of the experience of time. In relativity, the slowing down of time is a physical, measurable effect of speed, whereas the subjective slowing down of time during boredom is a psychological phenomenon related to human consciousness and perception. However, both reflect the larger theme of the relativity of time. Time is not an absolute, fixed entity, but a variable experience, whether through physical movement or psychological states. In this article, we will present a rich metaphorical exploration of the relationship between time, speed, and perception, using the analogy of a hot air balloon ride to illustrate the relative effects of increasing speed on temporal and spatial experience. The central analogy of a hot air balloon ride serves to visualize the expansion of one's perceptual horizon as speed increases. At first glance, this metaphor is quite effective in showing how speed changes perception, especially in the context of time. When we are standing still, equivalent to zero velocity, our perspective is limited to our immediate surroundings. In terms of time, this corresponds to the present moment, a normal-sized moment with a clear boundary, similar to the limited vision we have when standing on the ground. However, increasing speed, such as ascending in a hot air balloon, expands our perceptual horizon. From a higher altitude, a wider view can be seen. Similarly, a moving observer, traveling at relativistic speeds, can perceive a larger timescape, an expanded view of space and time. This is similar to how time dilation in special relativity allows for an expanded perception of the universe at higher speeds, where greater distances can be covered in shorter amounts of time. However, this expansion of the perceptual horizon comes at a significant cost. The higher up in the balloon, the less one can interact with the details of the landscape. This analogy captures an important aspect of relativistic physics. While increasing speed allows one to experience a larger swath of space and time, the ability to interact with those spaces and times becomes more limited. This interaction limitation is critical. While moving at higher speeds may give an observer access to a larger portion of space-time, as seen in time dilation, it also inhibits their ability to interact with the finer details of their environment. This paradox reflects a broader theme in physics, particularly in the study of quantum mechanics and relativity, that increasing the scope of our observations often comes at a corresponding loss of resolution. For example, Heisenberg's uncertainty principle shows that increasing the precision with which we can measure one property, e.g., the momentum of a particle, reduces the precision with which we can measure its complementary property, e.g., position. Similarly, increasing the temporal and spatial scope at higher speeds creates a tension between breadth and depth, sacrificing detailed interaction. The idea that moving objects perceive larger amounts of space in smaller amounts of time brings us back to the phenomenon of time dilation, a fundamental feature of special relativity. Time dilation refers to the slowing down of time for an observer moving at a significant fraction of the speed of light. As speed increases, time slows down relative to a stationary observer, creating an expanding moment in which more space is covered in less time. This phenomenon creates an interesting duality in which the increased perception of space coincides with a decreased ability to interact with it. This paradox is particularly important when considering the extreme relativistic speeds involved in space travel or motion close to the speed of light. At these speeds, an observer can travel enormous distances relative to their perspective in a very short time, yet be almost completely disconnected from the reality of the spaces they are passing through. Meaningful interaction with a moving object or environment requires synchronization of timescales. To truly know something that is not moving, one must immobilize oneself. To know something moving, one must follow it. This idea suggests that observers in different frames of reference experience reality differently. At the extremes of physical reality, such as approaching the speed of light or examining subatomic particles, our classical intuitions about space, time, and interaction break down. While time dilation allows for a kind of temporal expansion, it also imposes a kind of isolation in which the moving observer is cut off from the intricate details of his or her environment. This metaphorical isolation points to the larger limitations imposed by the nature of space-time. Framed in the context of both quantum mechanics and broader physical theory, temporal symmetry presents a complex interplay between reverse causality and timelessness. We will show that, although seemingly distinct, these concepts can be subsets of a larger, unified framework of timelessness, especially when viewed through the lens of modern theoretical physics. Temporal symmetry, in this context, refers to the notion that time can be reversed or traversed in both directions. This is in contrast to our everyday experience of time moving in a one-way forward motion. This two-way behavior of time, although counterintuitive, is a feature found in certain physical theories, particularly in quantum mechanics, where time symmetry appears in the form of CPT, charge, parity, and time symmetry. Events that can be governed by reverse causality may appear to us as violations of cause and effect because we are limited to our one-way perception of time. This is a compelling argument, and it serves to highlight an important limitation of human temporal experience: our inability to perceive reverse causality in a direct, experiential sense. However, reverse causality is not merely a philosophical abstraction. In quantum mechanics, certain interpretations suggest that particles can behave retrocausally, that is, that their states or interactions can affect the past. A notable example is the Wheeler-Feynman absorber theory, which assumes that radiation emitted by a source is affected by both past and future events. In this context, reverse causality manifests itself mathematically, even if it remains hidden from our everyday perception. Temporal symmetry requires a sequential passage through time, either forward or backward, while timelessness, in contrast, allows for jumping between moments without following a continuous linear path. Examples of these situations include retracing one's steps to find lost keys or recalling childhood memories. In the first case, temporal symmetry requires a step-by-step journey through time, while in the second, timelessness allows for a leap from the present moment to a distant moment without requiring continuity. This distinction is compatible with certain interpretations of quantum mechanics, such as quantum entanglement, in which phenomena suggest that particles can be associated across space-time without direct, local interactions. In such cases, the concept of timelessness, or at least a form of non-locality, can provide a useful framework for understanding these effects. Timelessness allows for the possibility that certain quantum correlations can transcend the constraints of the forward flow of time. For example, an example of a premonition about a plane crash could be interpreted as reverse causality, a future event affecting the past, or as an effect of timelessness, a sudden nonlinear access to information outside the constraints of time. We will introduce David Bohm's ideas about the vacuum state in quantum field theory. He described this state as beyond time, as he put it. In this context, the vacuum state is a quantum field configuration that has no meaningful concept of time. It is an entity that oscillates at a high frequency. Bohm's insight is consistent with the idea that the distinction between time and timelessness blurs at very small scales of space and time. Bohm's broader philosophical framework, particularly his concept of implicit and revealed orders, offers even deeper insight into the relationship between time and timelessness. In Bohm's view, the implicit order represents a deeper, more fundamental level of reality, where time and space are intertwined, while the revealed order is the manifest world of linear time and space that we experience. This duality between implication and explanation reflects the relationship between timelessness and time. Timelessness corresponds to the introspective order in which all moments coexist in a non-local, non-sequential manner, while time corresponds to the explanatory order in which events unfold sequentially and causally. We can draw on David Bohm's concept of intrinsic and explained order to explain how the now can be the intersection of both time and eternity. Bohm's ideas provide a metaphysical framework that locates time within a larger reality that is not fundamental but instead emerges from a deeper, timeless state, the intrinsic order. In this view, the present moment, now, is a reflection of a more fundamental reality that transcends time. Bohm calls this intrinsic order. This philosophical idea has a deep connection to quantum mechanics, where the behavior of particles often defies classical, time-bound intuition. For example, quantum entanglement shows that particles can remain connected across very large distances and respond instantaneously to each other's states. Bohm's implicit order provides a useful metaphor for understanding how such non-local effects can emerge from a deeper layer of reality that does not conform to the conventional flow of time. The discussion then shifts to the mutual constraint of time and timelessness, drawing an analogy to the continuous variables in physics, such as position and momentum in Heisenberg's uncertainty principle. This analogy is particularly apt in the context of relativity, where time and space are intertwined in such a way that increasing speed, and hence spatial displacement, causes time to slow down. This trade-off between space and time is a fundamental feature of the space-time structure described by special relativity, where the faster an object moves through space, the less time it experiences relative to a stationary observer. The analogy further emphasizes the inseparable nature of time and timelessness. They are inextricably linked, and our experience of one necessarily limits our experience of the other. The interaction between time and timelessness examined here overlaps with several fundamental themes in modern theoretical physics, from the reversibility of quantum systems to the time dilation effects of special relativity. Here we will discuss the fundamental nature of reality and the mysterious behavior of quantum systems, outlining a complex exploration of the interplay between time, timelessness, quantum phenomena, and consciousness. This synthesis reflects a multi-dimensional approach that incorporates elements of quantum mechanics, thermodynamics, and cognitive science while providing a framework for explaining phenomena such as temporal reversibility, entanglement, and consciousness itself. Let's begin by recalling the familiar tension between breadth and depth in the context of time, likening it to the trade-off between being a jack of all trades and a master of none. This analogy is framed within the constraints imposed by time. Pursuing breadth or depth requires a temporal investment, and the scarcity of time forces us to choose one at the expense of the other. This is a philosophical reflection on the larger relationship between time and space, and how our experience of them shapes our understanding of reality. Time fills space, and without the dimension of time, space itself would not be fully realized. This is consistent with the view of space-time in general relativity, where space and time are intertwined in a single domain. However, the reference here to the concept of timelessness introduces an interesting tension between space-time and a realm beyond it, where time as we experience it may no longer be dominant. The idea of stepping out of line to reach other points in time reflects the idea that there are ways to bypass the linear progression of time. This proposal overlaps with certain aspects of both mathematics and physics. For example, in higher dimensional theories such as string theory or the many worlds interpretation of quantum mechanics, additional dimensions beyond the 4 dimensions we experience could allow for phenomena such as time travel or instantaneous transitions across time intervals. The concept of stepping into timelessness is compatible with the timelessness of the photon. A photon traveling at the speed of light does not experience time in the same way that larger objects do. From its point of view, if such a point of view can be attributed to it, it does not experience the passage of time, but traverses space instantaneously. This is a direct consequence of special relativity. For any object moving at the speed of light, time expands to the point of timelessness. Photons, therefore, exist in a timeless state where all points in space and time can be reached simultaneously. The EPR paradox can also be cited here. This paradox challenges classical concepts of locality and causality because measuring a particle seems to instantly affect the state of its entangled partner, regardless of the distance between them. This paradox can be resolved by considering the timelessness of photons. Since photons travel at the speed of light and exist outside of time, the separation between two entangled photons may be an illusion created by our temporal perspective. From a timeless perspective, the two photons may be the same particle, and their seemingly instantaneous interaction may be a reflection of this fundamental unity. Thanks to quantum events, information can be sent back in time, and quantum collapses can contain information from both the past and the future. This retrograde flow of information could, in theory, explain phenomena of subjective experience, such as hunches or intuitions. In this context, the second law of thermodynamics, which governs the forward progression of time through increasing entropy, does not seem to apply in the quantum realm. Quantum systems, especially in their non-collapsed states, do not obey the classical arrow of time and can exhibit behaviors that reverse causality. Hameroff's suggestion that consciousness may contain quantum information from the future is speculative but intriguing and offers a potential explanation for certain anomalous cognitive phenomena recorded in experimental settings. In addition, we can also mention physiological evidence by Biermann and Radin, later followed by Biermann and Scholte, that could be interpreted as a kind of retrocausality or preconscious awareness of future events. In these experiments, subjects' physiological responses, such as skin conductance and fMRI brain activity, were measured before and after viewing emotionally charged or neutral images. In particular, the fact that subjects showed measurable physiological responses before emotionally charged images appeared on the screen suggests a kind of foresight or precognition that would challenge our traditional understanding of time. Skeptics argue that such effects could be the result of methodological flaws, statistical anomalies, or subconscious priming rather than true retrocausal effects. However, the possibility that quantum information could travel backward in time to affect conscious or subconscious processes is consistent with certain interpretations of quantum mechanics, such as the computational interpretation or the two-state vector formalism, both of which allow for time-symmetric or retrocausal effects. Furthermore, if closed time-like loops or other timeless structures exist, then consciousness would be provided with the framework for thinking about itself and interacting with temporal events in ways that are currently beyond our understanding. This idea, while speculative, lends support to the idea that closed time-like curves, paths in space-time that loop back on themselves. In general, relativity could theoretically allow for time travel or retrocausation. The role of consciousness in such a framework remains largely unexplored, but the suggestion that consciousness can access timeless information or affect events in time offers fertile ground for further theoretical and experimental research. While many of these ideas remain speculative and require further experimental validation, they do offer intriguing possibilities for expanding our understanding of both the physical universe and the nature of consciousness. Thanks for listening, and take care.